Next, we need to examine if the following sets are linearly independent. Okay, so let's do that. So we claim that the set is linearly independent. So what do? We take an arbitrary linear combination which is equal to 0, and we need to show that alpha and beta are equal to 0 in order to prove that the set is linearly independent. Equating component wise, we see that we get these two equations. So we will now show that alpha and beta are equal to 0. This we have just got merely by equating the components on both the sides, right? And this is a linear homogeneous system that we have. Okay. Now, suppose one of the alpha or beta is non-zero. Okay. So one of the alpha or beta is non-zero amounts to saying that it has alpha and beta has a solution. These two are the linear homogeneous system in terms of alpha and beta. So having one of alpha beta being equal to not equal to 0 is saying that alpha beta have some solution which is other than 0. Okay, that will happen if and only if the determinant of the coefficient matrix is 0 of the above system. Yeah, see, 0 and 0 are always the solution, but we have to show that apart from 0, 0, there is no other solution that can exist for alpha and beta according to these two equations. Okay, so one of the alpha beta is non-zero if and only if the determinant of the coefficient matrix of the above system is 0. But the determinant of the coefficient matrix is exactly AD minus BC, which is given to be non-zero. So it is a contradiction. Therefore, ABCD in R2 with this condition is linearly independent. Is it clear? Any doubts? Okay. Yeah. Next, we claim that the set V1, V2, so on till Vk is linearly independent. Please recall that the set Vi is 1, alpha I square, and so on till alpha I to the k minus 1. So we again we have the scalars a1, a2, so on till ak in R such that the linear combination is equal to 0. Now we need to show that ai equal to 0 for all I. We write the definition of VIs and equate component wise on both the sides to see that we get this equation. Please note that we need to show, in order to say that it is linearly independent, we need to show that all AIs are equal to 0. Okay. If possible, let not all AIs be equal to 0. Then it gives a condition on the coefficient matrix, as we saw in the previous part. Okay, it gives the condition on the coefficient matrix that the determinant of coefficient matrix is equal to 0, which is a contradiction. Why is it a contradiction? We have seen in tutorial 2 the determinant of the Vandermonde matrix. If you see here exactly, it is the coefficient matrix is exactly Vandermonde matrix in alpha 1, alpha 2, so on till alpha k. All right, and we know that the determinant of Vandermonde matrix is product of alpha I minus alpha j, and we know that from here we know that they are distinct real numbers. Therefore, the determinant can never vanish. Okay, but if any of the AIs take value other than 0, it will force the determinant of the Vandermonde matrix to be equal to 0, which is not at all possible. Therefore, whatever we assumed was not correct because we get a contradiction here, hence the claim. Okay, so we've assumed that let not all AI be equal to 0, but that forces Vandermonde matrix to be equal to 0. But by what is given, we know that the Vandermonde matrix cannot be 0 because alpha I is not equal to alpha j for I not equal to j. Okay, and therefore all the AIs have to be equal to 0, and hence the claim follows. Any doubt in this part? Okay, yeah. Next, we need to show that 1 cos x cos 2x so until cos nx is linearly independent. Okay. So again, the same thing we do. We let a linear combination to be equal to 0. And we need to show that AIs are equal to 0 for all i's from 0 to n. What we do for this? we use the fact that integration from 0 to pi cos mx cos nx dx is equal to 0 for m not equal to n. We use this fact. This we have proved in high school. You guys would have seen it. All right. So how do we obtain such a thing, such a form from here? We multiply it throughout in this equation. We multiply it throughout by cos x and we integrate from 0 to 2 pi. Okay. And then we see that the rest all terms will be 0 because cos mx cos nx dx is 0 for m not equal to n. Therefore, only the first two terms survive. And out of that also this is that happens to be 0. So here we get this condition. So after substituting the limits, we have this and it forces a1 to be equal to 0. Okay. Similarly, by multiplying cos 2x and so on, you can see that ai's are equal to 0. And please note that once all ai's from 1 to n are equal to 0, it will force only a0 will remain. So it will force even a0 to be equal to 0. And hence we are done. We also need to show that a0 is 0, right? But that will follow once all ai's for I ranging from 1 to n are 0. And therefore, we get that this set is linearly independent. And D is similar to C. You have to just take arbitrary linear combination, equate it to 0 here, equate it to 0, it's just sine instead of cos. The same formula holds even for sine, right? So you need to just go through the same solution, substitute sine instead of cos. Next, we need to show that this is linearly independent. So we let linear combination equal to 0. We need to prove that ai's are equal to 0 for I from 0 to n. Okay. So what do we do is that we divide throughout by e to the x. We divide throughout this equation by e to the x. And then we'll be just left with a0 plus a1x and so on till an xn. But we already know that they are linearly independent. But we still recall the proof. How did we prove in class that they are linearly independent? We differentiated I times. When we differentiated I times, all the terms before ai's, they will be 0. Okay. We differentiate I times to obtain that ai is equal to 0 for all I ranging from 1 to n. Next, so here, this problem is an application of the rank-nullity theorem that we have learned in class. So the problem says that let A be any 10 cross 10 matrix with A square equal to 0. We need to show that rank of A is less than equal to 5. All right. So you can clearly see that the image of A is contained in the kernel of A. Yeah, A square equals to 0 means A times A is equal to 0. So everything that is in image of A has to go inside the kernel of A. Okay. And what is the dimension of image of A? Dimension of image of A is rank and dimension of kernel of A is nullity of A. Okay, so from here we get this equation that rank of A is less than equal to nullity of A. By rank nullity theorem, we know that rank of A plus nullity of A is equal to 10. Why 10? Because it is from vector space is from R10. This is a linear transformation from R10 to R10. So the dimension of the domain is 10 because the domain is R10. So rank plus nullity is equal to 10. Using this equation, what do we know? We know that nullity is greater than equal to rank. So this, which is this, is greater than equal to rank plus replace nullity by rank by using this inequality. And then cancelling out 2, we get that rank of A is less than equal to 5. This is a small yet a very beautiful application of the rank nullity theorem. It can help us to guess rank and nullity of a matrix with some conditions on it. Okay. Next, we have 7th problem. Let A be 5 cross 4 matrix having rank 4. Then we need to show that AX equal to B has no solution when the augmented matrix AB is invertible. Let A be denoted by the entries small aij's, okay, 5 cross 4 matrix, and B be a vector in R5 such that AB is invertible. Okay, so we assume that AB is invertible, and we prove that AX equal to B has no solution. Let X equal to X1, X2, X3, X4 transpose be the unknowns of the system AX equal to B. We have to show that such xi's do not exist. Okay. What do is that we go by a method of contradiction. We introduce a new variable x5 and we note that AB. So what is this notation? We have just added one more column to A. All right, just as we do in the augmented matrix. We take the coefficient matrix. That's how we have done this. Okay, so we have this new matrix AB times Z equal to 0. This have a unique solution, namely 0 solution. Yeah, because it's a homogeneous system. Okay, so this system has a unique solution, namely 0 solution, where Z is equal to x1, x2, so on till x5. Now, let us assume that Ax equal to B has a solution. Let's say X. Then what will happen if this solution exists, that is if x1, x2, so on, x3, x4, if they exist so that they satisfy this equation, then this new system, corresponding to this new system, we have this equation. x1, x2, x3, x4 and minus 1 transpose. This will satisfy this equation. Okay, why it will satisfy? How did we get this? Actually, we have got this new system. Just here, if we look at this equation, we can write P as B times 1, right? B1 times 1, B2 times 1, and so on. And when that comes to left hand side, it gives us, its sign will become minus, right? It will be minus B1 times 1, minus B2 times 1, and so on. That's how we have gotten this. Okay, so clearly this will satisfy the new system. If at all Ax equal to B holds, then this will also hold, right? But we see clearly that this, what is this? This is a non-zero solution. This system, it is not possible for this system to have any solution other than 0. All right? This has a solution other than 0, which is a contradiction. Therefore, what we assumed is wrong. What did we assume? We assumed that Ax equal to B has a solution. This is incorrect. All right? So therefore, we now know that if the augmented matrix is invertible, then it has no solution. So please see that this AB is invertible matrix, right? So here it will force Z to have only unique solution, which is 0 solution. You can always multiply by this AB inverse. You'll get Z to be exactly equal to 0. So this system can have no other solution except for 0. Okay. Is it clear? Any doubts? We have last problem for the day. Before that, any doubts in any of the previous questions? Any one of you? You may unmute yourself and ask, or raise your hand, or type it in chat box. All right. So we move on to problem 8. Here we need to find a basis for subspace, this subspace. Okay. Let P be xy plane. We need to find basis of many vector spaces. Okay. Firstly, we have to find basis of W, which is characterized by these elements in R3. Next, we have to find out basis of W intersection P. We have to also find out a basis of the subspace of all vectors in R3 which are perpendicular to the plane W. So this question has got 3 parts. We will solve them one by one. First, we find out the basis of W. You see that this equation can be written in this form, where A times xyz equal to 0, where A is equal to this. When we multiply these two, we exactly get this equation. So the elements of W can be characterized by this linear system. First we observe this. Next, we see that the rank of this rank of A is exactly equal to 1, right? It is a non-zero matrix with a single row. So it has rank equal to 1. By rank nullity theorem, we know that nullity of A plus rank of A is equal to the dimension of the domain. Okay, here, what is the dimension of the domain? 3. Okay, so nullity of A will turn out to be equal to 2. We need to find out the nullity of this A, right? Nullity of A will give us all those x, y, z which satisfy this. We see that this is already in echelon form, okay, with pivot element sitting right in the first row, first column, right? So corresponding to the non-pivotal column, that is second column and the third column, we have two free variables. Let's name them as t and s. So let y be equal to t, z is equal to s. So what do we get? We get x is equals to 2t minus 3s by this equation. X will be equal to what? X will be equal to 2y minus 3z. Substituting the values of y and z in terms of these free variables, we get the value of x, right? So x, y, z, which is any vector in W, that can be written as t and s are the free variables, and now we have gotten x as linear combination of t and s. So we just substitute it here, and then we see that it is spanned by these two vectors. Note that t and s are free variables. That means I can choose t and s as any variable. They are free variables. So I have the freedom to choose these two as any two scalars. Okay, that's what is the definition of span, right? So we can clearly see that such kind of elements are spanned by these two. Okay, so therefore this is basis. This is the basis of W. Okay. Next, we find out the basis of W intersect P. Now we look at the basis of W. P is just the xy plane, that is z is equal to 0. So in these two, this element of R3 does not belong to xy plane, but this belongs. So in the intersection, only this will remain, right? Only this and span of these will remain in the intersection of W and the plane P, which is this xy plane. Okay. So therefore, clearly the basis of W intersect P is 210. Okay. This and hence the span of this does not lie. Okay. This and hence the span of this does not lie on the xy plane. This does not lie, and also the span of this does not lie. Please see that the span of this will be alpha times this. Okay. And we get the last component will be equal to alpha. So except for alpha equal to 0, no such element of R3 can lie on the xy plane. Therefore, neither this nor its any linear combination lies on the xy plane. Therefore, the basis of W intersect P is given by 2, 1, 0. Okay. Next, we need to find out the basis of the subspace V. So we define V to be the subspace of all the vectors in R3 which are perpendicular to the plane W. And then we calculate the basis of V. W is equal to span of these two vectors. We have seen this, right? So it follows that a vector ABC belongs to V if and only if its dot product or the scalar product is equal to 0. Okay. We have seen this, right? Any two vectors, they are perpendicular if and only if their dot product is equal to 0. Since W consists of all the vectors of span this and this, any element in V will satisfy this property. Any element of V is rather characterized by this property. Okay, so we see here that this will give us this linear system. These two equations give us this linear system. Yeah. We write it in terms of matrix and we get this. We can clearly see that this can be written as this. The system can be written as this. Okay. Now we find the REF of the above matrix. So REF of above matrix will turn out to be this. Now we see here that the pivotal columns are 1 and 2. So here we just have one free variable corresponding to the third column in this case. These two are the pivotal elements. The free variable is C equal to T corresponding to, we let it equal to T, which is corresponding to the non-pivotal column, which is the third column here. Okay, these two are pivotal elements. So the variable corresponding to this, which is C, is the free variable. Let it to be equal to T. And then we get 3 by 2b plus T is equal to 0 and 2a plus b is equal to 0. From where are we getting these equations? We are just getting these equations by this matrix. This matrix times ABC is also equal to 0. Solution doesn't change when we apply the elementary row transformations. Okay, this is one thing to be observed here. So we have got these two equations, and the above two equations again give us this. So here A, B, and C. Here we see that A and B are dependent on C. C is a free variable. And from here, these two values, we get from these two equations, we can get A and B can be gotten in terms of the free variable C, which is named to be T, which is set to be T. Okay, so we have all ABC in terms of T. And then T is out, T is common, and therefore we get it as 1 by 3, minus 2 by 3, and 1. All right, so this is a basis. Please note that here, every time while finding the basis, you need to write that this is a basis. Okay, because we know that the bases are not unique. Okay, there can exist many bases for a given vector space. So therefore, this term A is written with this intention. Okay, so I'm done with this tutorial sheet. So if you have any problems, you may ask me. If not, then I'll quickly go to the first part, which I promised to do if I have time. Okay, that is question number 3. Yeah. So let's look at the first part. The first part, we need to find the dimension of S. The first part says that P of 0 equal to 0. So clearly 0 belongs to S. 0 polynomial has 0 at all the values. Therefore, P0 equal to 0 is satisfied. Right. Next, we assume P and Q to be in S, so that P0 equal to Q0 is equal to 0. And this implies that P0 plus alpha times Q0 is equal to 0. Therefore, this particular element also belongs to S. Why this belongs to S? Because instead of replacing x equal to 0, I should get the value of this polynomial. Evaluation of this polynomial at 0 should be equal to 0, and that I'm getting because P0 is 0 and Q0 is 0. Therefore, I've showed that 0 belongs to S. Linear combination of any two vectors is in S. Therefore, S is a subspace. Okay. Next, we pick up any polynomial P in S. We impose the condition P0 equal to 0. When you impose P0 equal to 0, you see that only A0 remains. So it gives the condition that A0 is equal to 0. So now clearly, what all form basis? X square and so on till xn forms the basis for S. You know that this is linearly independent because the parent set 1, x square, and so on till xn is linearly independent. And also you can see by the very way we have taken px, that px can be written, px has a0 equal to 0. So px is exactly a1x plus a2x square plus so on till an xn. So px can be easily written as linear combination of these, exactly by writing summation ai to the xi, I running from 1 to n. All right. So it spans as well as this is linearly independent, which is enough to show that it is a basis. So it forms a basis, and we look at the cardinality of this, which is n minus 1. Therefore, the dimension of S is equal to n minus 1. Okay, so with this we finish almost all the problems of tutorial number 3.